Introduction. Welcome, everybody. I hope you're having a wonderful day, and thank you for taking the time to join us here. Today, we're going to be discussing an introduction to air barrier systems. This is a dense topic, and hopefully this is a foundational presentation for you to take some new insight into air barrier systems and understanding them, controlling air leakage and moisture movement. So a little bit about W.R. Meadows. Very proud to work for this wonderful company. We were established in Elgin, Illinois in 1926. We're 95 years old this year and proud to be going strong. Still to this day, we're a single family owned and operated American company, which is amazing, kind of within the group of companies that we compete with. We continued to grow since 1926 and brought regional manufacturing to all points in North America. And today we have 12 facilities in North America and 2 in Canada. We do also work internationally, and should you have projects internationally, we are very interested in assisting you, as well as we have a very strong network around the world. Here's a little bit about the Meadows family of products. We have a massive portfolio of premium grade building products. These are the general categories. Expansion joint materials were some of the first that we started with as a company, and actually today I believe the only ones still made in America, fiber expansion joint that is. We have a large portfolio of concrete restoration material, construction liquids, Division 3, joint sealants, and today we're talking about building envelope materials, but we have a full portfolio of systems for the building envelope: waterproofing, air barrier, thermal and moisture protection, vapor barriers, and we have a sister company, Blue Ridge Building Products, which provides soundproofing and insulation board as well. Should you want to learn more, I encourage you to take a look at our website. Very comprehensive and full of wonderful resources for you, architects, engineers, and those interested in the building industry. So today we are doing an AIA presentation. I will speak no further about the Meadows company specifically, about our systems and our products, and get into the non-proprietary information regarding an introduction to air barrier systems. So our objectives today are to define the types of moisture movement within the building envelope, including liquid, vapor, and airborne moisture. We're going to identify potential issues with uncontrolled moisture movement, and we're going to identify product types associated with preventing moisture infiltration, and identify design options to prevent moisture movement, and discuss the installation requirements for successful air, water, and vapor barrier installation. Again, just housekeeping: if you have questions, please put them in the Q&A, and we'd be more than happy to answer them as we're doing the presentation, and then we'll also have a little time at the end for questions. So getting into the presentation, this is a presentation about air barriers and the building envelope. So we're only going to speak about above grade air barriers, but moisture mitigation only works if all of the parts and pieces of the puzzle work together. So the underslab, the below grade, above grade, and below grade systems all need to complement one another in order for this air barrier system to work. So that being said, we just need to make consideration for all of those other parts and pieces of the 6 sides of our building in order to sort of thoughtfully discuss an introduction to air barriers. So as you read this quote, the demand for high energy efficient and durable buildings continues to increase. As a result, proper building envelope wall designs, component detailing, and wall systems performance are becoming increasingly critical. One of the key aspects of achieving a highly efficient and durable building is the ability to protect the building from unwanted air and water infiltration. So when we refer to this quote, what is it trying to say? Basically, a high performance building is one that is designed to perform maximize energy efficiency, durability, life cycle performance, and occupant productivity. Essentially, for it to last for the longest possible service life of the building and to be sustainable. So you can see our bullet points there: energy conservation, durability, productivity, and operational considerations, all part of a long-lasting and highly successful building installation. So in order to get into the introduction to air barriers, we kind of have to go back to our foundational information, the beginning of our understanding of moisture movement as a whole, as it relates to the earth where we build our projects, to the hydrologic cycle, the never-ending cycle of evaporation to vapor, to rain clouds, saturation, precipitation. Our buildings interrupt the rain as it hits the ground, percolates into the groundwater, and then runs into lakes, rivers, soils, and evaporates once again. So it's a circular activity of the moisture movement on the earth, and we need to understand each part and piece in order to accurately design for moisture mitigation. On the left, you'll see the bullet points of the different parts and pieces that we're going to go over in the hydrologic cycle that are kind of foundational to setting ourselves up for understanding how to design our air barrier system. So gravity, capillarity, vapor diffusion, air transport, and dew point. The most basic of being gravity, of course, pretty self-explanatory. Water falls from the sky. It's pulled by gravity, soaks into the ground. Our buildings, we create systems that lessen the wetting potential from the gravitational pull of moisture. So roof systems, eaves, gutters, siding, that sort of things, below grade applications of drainage. Capillarity is something we have to consider with moisture movement in the hydrologic cycle. It's the force that results from the greater adhesion of a liquid, water, to a solid surface, more so than the internal cohesion of the liquid to itself, and it's therefore able to literally rise along vertical surfaces. That means that liquid rises against gravity. It's kind of a scientific anomaly. It's one of many that's related to the compound of water. The amount of capillary rise is determined by the spaces between the particles. Or if you're looking at tubes, a tube with a smaller diameter will produce a greater rise. When selecting granular materials for drainage, larger spaces between the aggregate will reduce the potential for capillary rise. And of course, if we have a below grade structure and we have maybe our building above the water table, but we have a lot of sandy soil above that water table, we may see that the water is drawn up into our building envelope by small particulate matter. So we have to account for capillarity. Vapor diffusion, water vapor diffusion through a material results from the migration of vapor through a solid material as a result of the difference in vapor pressure, and it's important to take that in as a result of the difference in vapor pressure. It's important to understand that this is just a result of the difference and not a result of air movement. Based on the material, there can be different rates of movement, which translates in permeability of the material, usually reported in perms. And this permeability is dependent on the permeance of the material and its thickness. The more porous a material is, the higher the permeability. In this example, this was a study that was done in Florida. You can see the interior of the structure was 70 degrees and 40% RH. Over an entire heating season, a third of a quart of water diffused through a gypsum board. And we'll talk a little bit more about this in further slides. Air transport. So air transport is related to the hydrologic cycle and the movement of moisture over time. Moisture intrusion by air moves 70 to 90% of the moisture found in buildings. Vapor diffusion accounts for only about 10 to 30%, as shown in the previous slide. The last slide shown, as well as this one here, was from a study performed in Florida. They basically took a 4x8 sheet of gypsum board and ran it through a heating cycle through direct vapor diffusion. And a third of a quart of water came in for the gyp board without any holes in it. That's not a lot of water, but if you multiply that by 500 sheets of gyp board, that's a significant amount of water. So in this slide, you can see that if you were to punch a 1-inch hole in that board and you multiply the amount of moisture by 100, that's 30 quarts of water coming through your building enclosure. By looking at and understanding this study, air transport is responsible for quite a bit more moisture intrusion through openings in the building enclosure than by direct diffusion through materials in our structure. So dew point, an attempt to illustrate all of the factors of the hydrologic cycle and to understand moisture movement properly, we have to spend a little time on dew point and understanding what it means. In simple terms, air carries moisture in the form of water vapor. Relative humidity describes the amount of vapor. It turns to liquid water in the form of rain, or when that air comes in contact with something at the dew point temperature, the vapor in that air will suddenly become liquid water or dew, as we like to refer to it as. The atmospheric temperature below which water droplets begin to condense and dew can form is the definition of dew point. A simple illustration of this would be a cold glass of water on a hot day. As the glass sits in the humid air, the temperature of the glass below the dew point allows the glass to gather water vapor on its surface, which in turn becomes droplets of liquid water or dew. The elements in our wall structure need to assist in keeping the dew point temperature to the exterior of the insulation in vapor closed wall systems. And without getting too technical in this introduction to air barriers presentation, when allowing water vapor to pass through a vapor open system, we still need to control the elements in that wall system to allow the vapor to pass through without reaching the dew point inside of our wall system, and to ultimately then be properly conditioned by our HVAC system. For the great majority of buildings in all climate regions, nearly, keeping the dew point at 30 to 40 degrees during the heating season and below 55 during the cooling season provides a reasonable compromise between the competing interests of energy, comfort, and building durability. So this slide is just to reiterate the previous slides 12 and 13, that the vast majority of moisture moved into our building envelope is not through vapor diffusion, but mostly in large part from undetailed gaps and cracks and surface penetrations that allow the movement of air into our enclosure. Although this presentation places great focus on the small openings in the enclosure, it should also be noted that in large part, moisture movement by air is often overlooked in the design process when designing large service openings that also will need proper design. Consider a loading dock or double doors in an industrial space designed for daily use. Careful consideration of all large openings in the building envelope that compromise the intent of the air barrier system should also be considering your proper design of the air barrier. So now that we looked at moisture, the hydrologic cycle, the different factors that facilitate moisture movement by air, let's continue to look at air leakage and tie them in together. What is air leakage? And you can see from the illustration here, as described previous, it can basically be defined as the flow of air through gaps and cracks. This can be from the outside in or from the inside out as a result of different pressures. And from the standpoint of like a multi-story building, there are a number of different pressures that can result in air leakage, like wind, fan, and stack pressure. Stack being mechanical pressure, all resulting in air leakage if there's any holes, and there's always a few holes in each of our buildings. So looking at uncontrolled air in a cold climate, there can be a significant amount of heat loss as warm air is displaced by cooler air from outside, and then also air leakage of warm, moist air from the interior to the exterior can lead to condensation within the envelope, as we mentioned when discussing dew points as well. Not only can there be deterioration of materials, but there can also be reduced insulation performance depending on the type of insulation. So here's an illustration of the wind, stack, and fan pressure that we discussed earlier. Stack pressure and fan pressure is mentioned in our last slide, and here you can see it illustrated. So when looking at each of these independently, wind pressure occurs when the wind blows against the building and causes positive pressure on the windward side and negative pressure on the leeward side. In the northeast, of course, that would be the northeast side of our buildings, where the nor'easters blow would be the positive side of the building, and negative on the southwest, of course. Holes in the building can cause infiltration of unconditioned air on the windward side and exfiltration on the of conditioned air on the leeward side. Stack pressure occurs as a result of warm air rising, or more correctly, cool air sinking. And with an air barrier that isn't continuous, stack pressure can cause exfiltration at the top of a building of warm, moist air, and with the infiltration of cool air at the bottom. Obviously, stack
Well, I apologize. Apparently, our technical difficulties have returned. Give me just a moment here, and I will see if I can pick up and cover for Isaac while he tries to reconnect. Again, my apologies. Trying to catch up. I believe this is where Isaac left off in discussing air transport versus vapor diffusion. Again, I apologize for the technical difficulties. So discussing the difference and I guess to pick up, realizing that much more water is carried by air than by vapor drive. And that's an evolution of our understanding of moisture movement within the structure. And you can see by the illustration how much more water, up to 100 times, can penetrate into the structure. So air leakage becomes a major issue. It happens in very many places. This illustration gives a great detail as to what and where it can happen. When you start to think about small open areas and you know that 1-inch hole, when you look at this diagram, you realize that there's potential for literally thousands of 1-inch holes within our structures. So it becomes paramount that we understand this, detail these, and create a continuous system to prevent that air leakage. Obviously, air leakage can lead to very many problems, as we've discussed, including condensation within our structure that has some very negative effects. Here's some of the airflow examples, and maybe this is where Isaac left off. I apologize. But whether that be wind pressure, you know, which creates positive pressure on one side of the building and then negative pressure on the other, a stack effect, which can create upward pressure as hot air rises and creates higher pressure at the top, you know, in those critical places, particularly between the wall and roofing systems. It can be very critical in these installations. And then combustion and ventilation issues. Every time you turn the air conditioning or the heating system on, you change pressure levels. So, Isaac, are you back?
Yes. Sorry about that. A little computer crash here.
I'm going to try to get you back in as presenter.
Hey Roger, it's Conley.
Yes.
While you have the presenter role, if you share the file, upload the file under that more options, then if he crashes again, we won't have to switch screens. You can just continue off of the uploaded presentation. Do you remember how to do that?
No, not right now.
Click on share, scroll all the way to the bottom, share file, and then the file will be embedded into the meeting. So if we lose Isaac again, we can just pick up where he left off.
All right. Yeah, my problem is locating the file.
Oh.
If you want to just share, give me the presenter, I'll share my file again, and then I can just keep going.
Should be yours now.
Okay. So we were just talking about wind fan and stack pressure. Let's talk about air leakage again. This slide is supposed to give you a little levity. Could probably use it right about now. Theoretically, air leakage is fairly easy to deal with. Just stop the flow, but realistically, it's easier said than done. Just think about how many transitions, openings, materials, changes of plane are within a typical building, and then come up with a system that can provide continuity. So why stop the flow of air through a building enclosure? Bullet points say it best: function of the building, comfort and health of occupants, increase the life cycle of the structure, efficient systems reduce energy waste and create sustainable buildings, and according to the AIA, water infiltration is the leading factor in post-construction litigation. So we want to avoid being that gentleman with the hands on the head and pink tie there in court, trying to figure it all out later. Some building issues, of course, with moisture infiltration. We can see here efflorescence, mold, top middle, probably exfiltration in some natatorium where we have warm, moist air exfiltrating into a very cold environment and freezing. This, of course, will deteriorate bricks quite quickly and our facade fails. And then the big mold factor, which is clearly illustrated here as well. So why stop the flow of air through the building enclosure system? It's pretty simple. Again, through the bullet points, airflow affects the location of the dew point. Air leakage causes the HVAC system to work extra hard and creates unsustainable buildings. And for those of us in urban environments, we know better than anyone else that airflow is a vehicle by which sound travels, particulate matter becomes a problem. We can see dust on our desks, and airflow is a vehicle by which odors and gases, and of course, in the urban environment, we know all of these things very particularly. So air barriers cannot be dealt with without an understanding that they are part of a wall assembly. That's by one of our first air barrier pioneers. And we're going to discuss this a little bit further as we get into the different types of wall systems and looking at them. So now that we've looked at what needs to be controlled, how's this accomplished? It's done by incorporating control layers within the structure. So looking at a typical wall, there's a structural component you can see here. And looking at a typical wall, whether it's CMU, as you can see here, they all incorporate the 4 control layers. So typically it would be CMU is the backup, steel stud and gypsum or wood frame. On the exterior, there's cladding or brick panels, and then there are 4 control layers incorporated. The water control layer, of course, reduces wetting potential due to moisture intrusion. This consists of strategies to allow for deflection of the water, as we discussed earlier. The air control layer stops uncontrolled airflow through the gaps and cracks. And the vapor control layer reduces the movement of water vapor as a result of the difference in relative humidity and temperature. And this may or may not be required based on climate and wall design. But if it is included, proper placement of the layer is important to avoid moisture problems. And then the thermal control layer resists thermal transfer through the building enclosure. The use of this layer not only provides occupant comfort, but allows for control of the dew point within the enclosure and by maintaining temperatures above the dew point temperature within the interstitial space. Care needs to be taken in placement of the insulation so as to avoid thermal bridging. And with changes in building codes across the country, the use of a continuous insulation layer on the exterior incorporates this to address that. So here we see a little bit less of a resilient wall. We call it the less costly wall from a material and labor perspective. Rather than an interior wall of solid concrete block, an economic sort of choice would be the replacement of metal stubs of 2 metal studs, and gypsum wallboard and exterior grade sheathing is utilized. This wall has almost the thermal and moisture benefits of the perfect wall as we saw before, but it lacks the moisture sink provided by the concrete block. As in the earlier side, you can see though that all of the 4 control layers are incorporated here. So we're getting into the meat of this presentation. Where is the air barrier located? Well, this is one of the most poignant questions of the day. You could read a white paper on permeable versus impermeable, debate with exterior wall consultants on the subject in your own time, but the fundamental answer is it depends. A little smug, but it's very true. The placement is based on your hygrothermal region, the letter of the building code that's in your local jurisdiction, and largely on the design of your wall system. This presentation is meant as an introduction to air barriers, and so we're not going to spend a ton of time on this specific question, but maybe the question should really be posed, where is your air barrier located? So going back to what we had mentioned previous, in order to overcome the issue related to air and moisture movement, incorporation of the 4 control layers into the wall assembly is important. This could be one material or a combination of materials, depending on what material it is. Selecting which material is dependent on a number of factors, as discussed on the following slide here. But the illustration in this slide serves to illustrate the 2 types of air barriers that are incorporated in wall assemblies and how they would be placed. The left illustrates a flow through assembly with a vapor permeable layer as the air barrier, and the right is an illustration of an impermeable layer placed in a wall system as a vapor impermeable layer that serves as both an air and vapor barrier and drainage plane. So the essentials of an effective air control layer. Performance characteristics are all sort of laid out here. It's got to be continuous, all joints and laps and seams airtight. It's got to be durable for the life of the building. It's not a maintenance product. Once the wall is sealed, it can be very expensive to open it back up once there's an issue, or you may not even see the issue until significant damage has been done. So it has to be durable, it has to be strong, be capable of withstanding positive and negative wind, fan, and stack pressure, as I mentioned earlier, and withstand these intense conditions on the construction site. It's got to be resilient, so it has to be flexible in nature to allow for different substrate movements, expansions, and contractions. And let's get into the layers of an air barrier system. As mentioned, the control of airflow needs to be addressed by a complete air barrier system. A membrane installed within the assembly is an integral part of the system, but it's just a part. Looking at this chart, air barrier materials combine with other materials and components to make it up what's called an air barrier assembly. Air barrier assemblies then combine to make up the whole air barrier system. It's imperative that the air barrier system be completely continuous, and we'll get into that a little bit more. So again, going into the layers of a system, just a look further here at the layers. The assembly, as mentioned earlier, all of the transitions and major service penetrations and openings play a major role in this air barrier system as well. For instance, you won't receive any air movement below grade, but the transition from below grade to above grade is an opportunity for air leakage. Mechanical systems can draw in gases and air from our below grade system, and if they're not joined together correctly, we don't have a continuous system. So we're going to get into types of materials. There's a number of types of air barriers on the market today, consisting of sheet goods, mechanically fastened membranes, fluid applied membranes, as you can see here, polyurethane spray foam. All of these, when installed correctly, can function as an air barrier within a wall, and depending on the type of material, can also function as other control layers in the wall. For instance, a self-adhesive asphalt membrane would be the liquid, air, and vapor control layer in an assembly. So another fun question of the day: do you need a vapor barrier in the vertical wall assembly? Short answer is no. The illustration in this slide serves to illustrate the two types of air barriers that are incorporated into the wall assemblies and how they would be placed. Left illustrates a flow-through assembly with a vapor permeable layer as the air barrier, and right as an illustration of impermeable layer placed in a wall system as a vapor impermeable layer that serves both as an air and vapor barrier and a drainage plane. Again, as discussed earlier, this is really one of the most poignant questions, but the fundamental and long answer is still, it depends. The placement is based on your hygrothermal region, the letter of the building code that's in your local jurisdiction, and largely on the design of your wall system. The placement of the thermal layer and its values, and generally the components that will make up your wall assembly. This presentation is meant as an introduction to air barriers, and so we're not going to spend a ton of time on the specific question, but I guess to reiterate, the short answer is no, you do not need a vapor barrier incorporated into every wall assembly and into every air barrier material. So the types of air barrier materials, starting with self-adhesive, they come in permeable and non-permeable, and most non-permeable will require a primer. Most permeable will not. The benefit would be uniform thickness. As you can see, the penetrations might be difficult in some of the further slides, but in this photograph, a self-adhesive asphalt membrane is the air vapor control layer within the assembly. This is where you would see that it would be hard to put a peel and stick membrane down with all of these brick ties, but in some cases it's necessary. Fluid applied material or non-fluid applied material, they're monolithic, they're easy to detail. They're applicator dependent though for the factory thickness, and are they come in so many different chemistries, from acrylics to polyethers to STPEs and silicones. There's many options that are available, but we want to make sure that they're compatible to the types of materials that they're going on top of, and also the types of materials that they're being tied into. So they're easy to install. You can spray or roll them. They're easy to detail. They're less labor intensive. However, in like urban settings, you have to consider overspray, and the product doesn't solidify quickly. You can get it on buildings or cars or surrounding things. And also temperature, wind speed, whether you're above or below 40 degrees, when it's going to rain next, how long your material can be exposed. There's lots of different things that we need to consider within a fluid applied material application. Looking at it from a product consideration standpoint, we'll go through these bullet points quickly. Of course, we want a track record, some legacy, I like to call it, of the product being used and installed correctly and usefully within your region. Of course, you want to have a little bit of history of the project being successful. And then, of course, your local code requirements are important. This gets dicey when we get into cold weather applications, because some of the primers, depending on your code and your jurisdiction, may or may not be VOC compliant. So picking a product that's locally compliant is important. Cost, you want to think about your labor costs, your materials, and your time in the type of product that you're picking. Sometimes a peel and stick product is going to take you a little bit longer, but again, in an urban environment, you might have to go that route, or a combination of the two. You want some manufacturer support. Get us involved in your air barrier applications. Get us into the design process and into the mock-ups, and also have us out for the installation process. We want the materials to be compatible. As I mentioned before, there's lots of different formulations. Simple things like silicones and urethanes don't mesh well with asphaltic material. And then we, of course, need to consider the project and site conditions. Again, time of year, how long it's going to be exposed, what type of weather we're going to be dealing with, as illustrated in the rainfall resistance below. And then, of course, puncture compensation is important as well. Air barriers as mechanically fastened board stock. This is a large portion of how we see air barriers done. If you look at the Dow Thermax photo there on the left, all the seams have been addressed correctly. This is still an effective way to do an air barrier. However, it's not if we are not detailing it correctly. It's worth mentioning here that mechanically fastened film materials are considered an air barrier, and we only see these in wood-framed multifamily and some storage buildings, because it's only connected through the gasketed nails. A breach in the membrane may deposit moisture all the way down to the wall, and once an issue occurs, it can be very difficult to trace where that issue actually stems from. And as a manufacturer, we would recommend looking at all of your options for air barrier materials. However, this does fall into the category. Spray foam, considered kind of the holy grail of air barrier materials. These come at a considerable cost, but they do come in both open and closed cell, meaning permeable and impermeable formulations, and perform very, very well. So it's quiz time. Which one of these is not an air barrier material? Surprisingly, they're all air barriers. The slide illustrates that almost any construction product can be an air barrier, even the gum wall. There are many products that can function as an air barrier, and air barriers need to be strong, be capable of withstanding positive and negative wind, fan, and stack pressure, need to be durable, need to be continuous, all joints, laps, and seams, resilient, be flexible, compliant, and allow for differential substrate movements, expansions and contractions. But as you can see with the inclusion of some of these material like gum and peanut butter, the code doesn't always dictate the correct solution. Sometimes our creation of the air barrier system has to become performance driven and be designed to withstand the forces acting against it, as well as being durable and resilient for the service life of the structure. So merely picking a material to stand in to cover the code requirements will not address the potential for moisture movement properly and may leave you with an assembly worth nothing more than a wall covered in peanut butter. That's right. Merely picking a material to stand in for local code requirements may not adequately address what we're trying to impart in the presentation. Creating an air barrier system and assembly that will be strong, durable, and resilient and last for the entire life of the structure, it will take some extra effort on your part as designers to make this happen. So how and where do you use the different parts and pieces, transition membranes? Because they allow for movement, you should be using them on joints that are wider than 1/4 inch, though in some cases a tape is adequate. When there are gaps in the substrate material, such as chipboard here, they should be taped or sealed or filled with some type of joint filler. Mastic is ideal for covering edges of the substrate materials or joining the air barrier to rough openings. And some membranes require that the substrate be primed. This helps reduce dust and creates a better bond between the membrane and the substrate. And in some cases, term bars are used to reinforce the adhesion of a sheet membrane. This is the belt and suspenders approach. If you use those extra things like the termination bar, you're putting yourself in great company for success. Design of an air barrier system, simple designs get built right. I think the picture in this presentation here is meant to illustrate that the more material and transitions and types of things that we add to our design complicate the matter, and in order to create a seamless installation, let's try and keep it simple. So decide which layer of the construction provides the air barrier, stick with this, and use the pen test. We'll talk about that in the next slide to check continuity. So there can be more than one material that makes up the air barrier system. Tracing a pen along the line of the air barrier on the drawing will show if it's continuous or not. If you lift up the pen, then there's probably a disconnect and you need to create some type of joinery there. So minimize the number of types of construction within the envelope. Pay careful attention to the design of junctions between elements. Favor simplicity over form. Minimize the penetrations of the thermal envelope, and whether by service structure or construction. Each of these, as we open it up, creates discontinuity. So where penetrations are unavoidable with soil stacks or ventilation exhaust, intakes or water supply, electricity and gas supplies, develop appropriate details for the proper execution or for making good damage to the insulation and for resealing pipes and ducts around the air barrier. So we'll talk a little bit about specification. Of course, it's worthwhile to hold the air barrier specification, making sure that the products you researched and selected are the ones that you use. In creating your spec, take a look at the product's conformance to ASTM standards. Select a product that has a proven track record, and whenever possible, select an entire system to ensure compatibility and, in some cases, warranties. If you decide to use two different products together, one manufacturer's sheet membrane and a different manufacturer's transition membrane, be sure the two are going to be compatible. As an aside, calling out ASTM C1280, for instance, can really assist in holding sheathing installers really to prepare the substrate correctly in order to install a perfectly taped assembly with no gaps or cracks. And similarly, ASTM E2178 and E2357 can assist in determining the permeance of a material or the whole assembly. And try to remember the peanut butter wall example, and also that the point of the code is only to provide a weather resistive barrier. And it's up to you to provide strong, durable, continuous, and resilient systems that will last the service life of your structure. So plan review, this is a little bit more on the pen test. Let's go through the design and install process step by step. we'll start with the process of drawing the air barrier. The saying goes, the designer should be able to trace the air barrier with the pen, illustrated here by the red line. If you lift up the pen in tracing the building, we're going to have to create proper detailing. It's ideal if the designer can take the time to draw the joints, the corners, the meeting of the different materials. The best of all, the design team should meet for plan review of the air barrier assembly. And without this kind of detailing, too much is left to chance and the ability of the installer. And that can make mistakes and change orders frequent. Designing for tricky parts. I like to put this in here to remind you that as your designs become more and more complicated, it is very important to continue the detail of these designs in detailing and creating continuity. So all of these transitions in these tricky parts of the buildings that we design are very important. We'll talk a little bit more specifically about these details that are sort of bullet pointed here on the left, the roof to wall and foundation to wall, wall to door. All of these very important to actually spend time designing and making sure that we can install correctly. Mock-ups, spending time on the front end and specifying correctly will really help these get built. I like to use the example of the Frank Lloyd Wright houses. I love touring Frank Lloyd Wright houses whenever I'm in the area of one. And although very beautiful, most of them leak and are constantly being repaired. So again, it's important to develop these details early on to create successful installation. And as our buildings become trickier, it's harder to realize that. Pre-installation meetings are very important as well. Discuss the details for airtight transitions and connections. We want to discuss sequencing, design the details, and then define the expectations. So substrate prep is also very important in proper air barrier design. Ensure that the materials being joined together are compatible. This is kind of reiterating some of the points that we made earlier. But pre-installations, meetings, especially put into specification, can create resilient assemblies. Installation considerations. We'll go through the bullet points again. Number of joints, substrate condition and prep, the building location. Again, these are kind of reiterating what we spoke about earlier, but kind of trying to drive home the point that all of these different things really need to be considered properly in order to create a resilient and useful air barrier situation. So the environment largely is going to determine what types of materials you're using. The installation sequence is very important. Coordinating details with other systems. The roof to wall connection, I'm going to mention that later, but that might be the most important one that you actually spend time on, as well as the air barrier to below grade waterproofing. Connecting those two can mean success in your building service life. Number of penetrations is important. If we're doing a complicated cladding system, understanding how we're going to address the penetrations of the air barrier layer is also very important. And of course, rough openings. Substrate prep, substrate conditions, things to be aware of. The backup wall has some bearing on the best choices for your air barrier material and its application. Concrete has to be fully cured and smoothed. Beware of sharp edges and splinters common with wood substrates. OSB is one of those ones that's very difficult. Sometimes has splinters and has to be prepped correctly and primed in order to receive the air barrier material correctly. Glass face gypsum. Consider texture and porosity dependent on the fiber matrix and the chemical binders. Smooth walls with patching compounds if they're rough. Remove all formwork. Address control joints and shelf angles. Beware of staples and moving in different sheathings. And prep the substrate spend your time on the substrate and you will successfully apply your air barrier material. Connections. Transition membranes are required over all dissimilar materials. They must withstand the same sort of loads that the air barrier materials without displacement are going to be put up to. Compatibility is an important factor when choosing your transition materials, and they have to be able to accommodate all types of movement and spend time again on compatibility. That's an important one. Knowing simple things like urethanes and silicones don't pair well with asphalt will help you. And, spend time on those different types of materials that you're going to join together. Make sure they're all going to connect together properly and don't leave that up to chance at the last minute. So we're going to get into some of the specific details. If it's hard for you to take a look into these details, please do send us an email at the end, and we'd be more than happy to share the presentation and talk through some of the difficult details. Again, these are the important ones that come to bear when we are creating a strong, continuous, and durable, resilient air barrier system. So the roof to wall connection. According to building science studies and building failure forensics, this might be the most important connection you make and design. Let's address some common details and best practices. So wrapping the parapet prevents air leakage into the ceiling and connects the roof and wall. In this case, the air barrier comes up from the wall and wraps beneath the roof assembly. This is good. Air from the interior won't penetrate the roof assembly, bringing in moisture and potential for corrosion. You'd typically use a peel and stick membrane here in conjunction with a metal trim over the parapet. So you want to use a high temperature formulation. If you manage to properly connect your roof to the air barrier system, you'll definitely set yourself up for the long service life of your building that you had planned for. If you'd like to spend a longer period of time looking through these details, again, I'd be happy to share the presentation with you afterwards. Penetrations, very simple. Don't make holes that you don't need. Boot all the pipe penetrations, goop it up, fill them up, detail them. Remember that 1 inch by 1 inch hole and the amount of air that's then introduced into our building envelope. Spend time creating details for each of these service penetrations in the envelope. Very simple. I may have mentioned a little bit about self-sealing membranes earlier and how membranes can self-seal, how no membranes can really self-seal, around dozens of screw holes. And to reiterate, as you drive screws into the air barrier assembly, they remove minute portions of the barrier. They create a wider hole that can't be self-sealed. And even the most careful air barrier installation will leak when penetrated by dozens of screws used to attach Z-girts or furring and other types of attachment mechanisms for cladding. So ideally, workers will squeeze a bead of sealant into the penetration before placing the screw. In reality, this sort of thoroughness is rare unless you have close supervision on site. And a better solution may be to use fasteners with a neoprene gasket or strip or some type of ASTM test to hold the installers, to properly install them. Some of the ASTM tests you might want to incorporate are 1970 for water sitting on horizontal, and then for E331 for vertical and pressurized test. And then we can see properly installed fasteners here, detailed correctly. It's important to spend time thinking about how they're going to be incorporated into your specific wall assembly. Shelf angles. Not going to go too deeply into this, but here's a number of important details following this one as well. The shelf angle, where the main membrane is fluid applied. You can see here it's then overlapped with a through wall flashing that's a sheet good. A backer rod and sealant are incorporated under the drip edge, and then a bellows of sheet good transition membrane is tied in. again to the main fluid applied air barrier to maintain the continuity of the air barrier for this shelf angle detail to be continuous and create the perfect detail. Again, it's important to note that your air barrier here is a number of parts and pieces: fluid applied material, transition material, a tape drip edge with a sealant, a backer rod, and accommodation for the proper movement and openings in the assembly. Base of wall, another important connection here to work out in your drawings. Maybe what I would call the second most important after your roof to wall connection. On the left, the transition above grade with a sheet to liquid good. And then on the right, we realize an above to below grade connection with a post-applied waterproofing extending above grade to be covered by a peel and stick through wall flashing. You can see how the waterproofing membrane acts as a through wall flashing between the brick cladding and the foundation, and the transition membrane overlaps both the liquid air barrier, the post-applied waterproofing membrane, and the metal drip edge counter flashing to create a seamless transition from above to below grade. Sheathing joint treatment, important to detail joints properly, whether with liquid flashing or tape. And in gypsum sheathing, the installers could use that ASTM C1280 to help hold them in account and create strict guidelines around the gaps so you can properly install your air barrier system. Expansion joint treatment. At expansion joints, provide an extra bead or bellows, as you can see in the bottom right here, to give the membrane room to move with the building. That bead should overlap the building at each side by about 2 to 3 inches and loop inside or outside, and alternately, preformed systems are really good as well, as you can see on the left. Rough openings, jambs, and sills. Again, we can do these with liquid, with a combination of liquid and peel and stick. There's so many different types of formulations. STPEs, permeable, non-permeable. Compatibility with the PVCs and windows is important. Again, without getting too technical on these jambs and sills, it's very important to work out the details, though. And simply put, if you're going to go with a liquid flashing material, many of them are STPE formulations. Not all manufacturers have them, but those formulations work very well in combination with a peel and stick product that has an aluminum facer that's impermeable for the sill. That way you avoid failure. Building forensics shows that the sills are often a point of failure within a building. And if we put a peel and stick material on that's impermeable and we use an aluminum facer, we don't have to think too hard about compatibility, as that aluminum facer kind of works with everything, and the STPE system as well with the liquid flashing. Rough openings for self-adhesive material. If you choose to use a sheet membrane in rough openings instead of a liquid flashing, here's the steps to follow. So you would prime the area as recommended by the manufacturer according to the substrate, and then pre-cut the membrane to ensure the ease of handling. So you're going to cut all of your pieces for the 4 different sides, and apply first the pre-cut strip at the base of the rough opening, rolling firmly into place. Ensure a minimum of 3 inches extending onto the wall and into the rough opening, and ensure all edge overlaps are a minimum of 2 inches and end-to-end overlaps are 4 inches. And then you would seal the terminations with mastic, as you can see clearly illustrated on the right. So liquid flashing, an alternate option to self-adhesive, as I mentioned earlier, would be liquid flashing, which provides many benefits, including less cost on labor. They're quick to install. The STP formulation is a premium grade material with a long service life. Just a lot of compatibility with the STP liquid flashing formulations as well. They can be used in conjunction with a peel and stick, as I mentioned earlier, And usually with an aluminum facer, you don't have to think too hard about compatibility at all. Construction damage, we're going to talk about next. In all instances, with all types of membranes, fluid, or sheet, there's a risk of damaging the material in multiple ways, whether that's from another tradesman not really treating the material correctly before it's protected, or the product itself not being installed properly. All materials can become damaged on the job site. So early rain can damage a fluid applied air barrier. The rays of the sun can ruin all types of materials if they're left exposed beyond their service life. And in all instances, knowing the capabilities of the material and treating the damage before the installation is covered is just as important as proper installation. Poor workmanship, unfortunately, is a reality of every part and piece of our projects. Job site damage isn't the only way that material and system can be compromised. Improper installation actually takes a higher place on the list of things to look for when it comes to air barrier assemblies. And it's important to make sure that we have the manufacturers out there and create opportunities in our specifications for making good on these damages. UV exposure, as mentioned earlier, is an important part of all air barrier material. Knowing how long it has to be covered up or how long it can be exposed before it's covered up is very important. And that wraps it up. As air barriers are an essential part of a building's energy and savings and durability, we need to spend time designing them correctly. Let's select materials and systems based on project requirements, and hygrothermal region is largely going to determine the types of materials that you use. And an air barrier installation needs to be addressed during design stage, and all factors need to be considered. The performance of a system is dependent on the details. Don't forget that roof to wall and above to below grade, very important parts, and consider materials and systems that save time and proper installation. So this concludes the AIA portion of our presentation. I thank you all for your patience during the technical difficulty and the crash of my computer today. I really do appreciate your time here. And if we have some questions, Roger would be more than happy to spend a little time talking with those that are able to remain to go over some of the information. Thank you again for joining us. I look forward to seeing you on our website, or give me a call over the phone. My email is there, my number is there, and we have some wonderful resources for you here at WR Meadows.
Great job, Isaac. Thank you very much. We have run over, and quite frankly, there are more questions than you can imagine. Great job in keeping your focus through all those technical issues.
We do what we can, you know.
that's been our nightmare throughout all of this for the past 18 or so months, or 15 or so months. Rather than try to pick out questions, I think that there are many that are very specific. So since we have run over a little bit, I'm going to beg for our audience's permission and patience. And we'll reach out to you individually and address your questions in the next couple days.
We certainly will. And I just wanted to jump in here and say we will answer all of your questions. Definitely. We will get to you. It's actually one of the things that we enjoy about these large presentations is we do get quite a few, and it gives us an opportunity to interface with you as well privately. So thank you for your time and attention here today.
Yeah, thanks everybody. Really appreciate it. Look forward to seeing you down the road. Thanks again, Isaac. Great job.
Thank you so much. You have a wonderful day, and do check out our website when you get a chance. There's a lot of resources there for you. Thank you for your time. Take care.